A force can be casually described as a push or a pull. Force is a vector quantity, and it's given the symbol F. To analyze forces, we'll use what are called free body force diagrams. These are tools used in physics to analyze the forces acting on an object or system. In a force diagram, it's good technique to let every force vector be labeled in agent-object notation. The form of agent-object notation is shown below. The agent is who or what is doing the pushing or pulling on the object. The object is who or what is feeling the push or pull. The term system refers to an object or group of objects enclosed inside a physical boundary. The term surroundings refers to anything that's outside the system. It can be anything in the environment that might significantly affect the system in any way. In the drawing below, what is considered the system? Since conventionally systems are enclosed within dashed boundaries, I would say the log is the system. What are the surroundings? That would be anything that's not the system. We could have the tractor, even the rope that is attached to the log, the ground, the air, and there are many other things we could mention as well. Now let's draw all the different forces acting on the log below. The first thing to do when you're making a free body force diagram is to place a dot in the center of the system. And now we're going to add arrows to that dot. The vectors will represent the pushes or pulls that the system might be feeling. So there's one thing that always pulls on objects near Earth's surface, and that is gravity. Earth pulls directly downward on all objects that have mass. So that'll be our first force. Let's label it now. We'll start with big F to make it clear that this is a force vector, and then it's good to say what type of interaction it is. This is what's called a gravitational force. It's a long-range force, one that results from the system's interaction with force fields of some kind, such as magnetic, electric, or gravitational fields. And physical contact actually isn't required for these forces to act. So we'll put a little G there. Next, I'll say who is doing the pulling. That's Earth. And then we'll say on. And then we have to write who is feeling this pull. We could put log, or perhaps system, because the system is the log. What other forces might be occurring? Anything that the log is in contact with, perhaps? Well, there's a pretty taut rope here. It's pretty tight, so chances are it is exerting a force on the log. We can't tell for sure, but I'll bet it is. In many cases, it would be. So let's draw that force. Now notice here that I drew the gravitational arrow down because Earth pulls objects down. So which way is the rope pulling on the log? Because that's the direction we want to draw for our force of tension. Of course, it pulls the log to the right. So we want to show an arrow to the right indicating that the log is feeling pulled forward. Now let's label it. And what type of interaction is it? Well, this is going to be a force of tension. It's a contact force. And for a contact force, anything that results from contact between a system and the surroundings at the system's boundaries should be included. These forces could include static and kinetic friction, tension forces, and normal forces. This would be classified as a tension force, so we'll use the letter T for that. And I'll say that it is the rope pulling on the system. Tractor is connected to the rope's connected to the log, so really the rope is the thing that's directly acting on the system. Are there any other forces at play here? Anything else that the log is in contact with, perhaps? Notice that the log is in contact with the ground. The ground can supply a force as well. Which direction, though? Well, the ground stops the log from falling. If the ground wasn't there and there was just an empty pit, the log would certainly fall. The reason it doesn't fall is because the ground is supplying a normal force. Normal forces act perpendicularly to the surface that's in contact with your system. So seeing as how the ground here is along the x-axis, then the force will be directed along the y-axis, perpendicularly to the surface. Now this is going to be a normal force. We'll give it the letter N. Normal is from a surface. And we'll just say ground or earth on system. Okay, that's 3 forces. Are there any other possibilities here? There could be other things as well. There could be, for example, air resistance. There could be friction. We don't know how much friction or air resistance there may be. But I'll go ahead and draw the direction that friction would act if there was any. Friction will want to stop the log from moving forward. It'll push in the backward direction. And friction gets the letter F. And again, it'll be the ground on the system. So as you can see, there are many possible forces that could be at play in a situation like this. And even the force that the ground exerts on the system could be directed in many different ways.